In the previous lectures, we investigated the noise characteristics of an optical receiver. We calculated a parameter, what is called the bit error rate or BER, which depends upon the signal to noise ratio of the optical signal. We also saw what is called the quantum limit of detection. That means, in the absence of thermal noise, just because of the statistical nature of the photons, how much minimum number of photons are required per bit to get a bit error rate of 10 to the power minus 9. We saw that this limit is very small. So, in practice, we will not be able to go to that level, but in a hypothetical situation, suppose we make the best possible receiver where the thermal noise is negligibly small and the short noise is the one which affects the signal to noise ratio performance, then how much minimum power one should receive to get the required bit error rate. Now, when we are doing all this analysis, we essentially assume the ideal receiver. What that means is that when 0 level is transmitted, we assume that the 0 level corresponds to 0 power. Also, we assume that your clock is very, very stable. We assume that during one level, the amplitude of the light intensity remains constant. Now, all these are very hypothetical or ideal situations. In practice, we always have deviation from this ideal situation. That means, corresponding to 0 level, we do not have a condition of no light, but there is always some light transmitted even during 0 level. Also, because of the laser noise, we have fluctuations of the optical signal during level 1, and also we do not have a very stable clock. So, now one can ask a question that if the receiver had deviated from the ideal conditions, then what we have to do to achieve the same receiver performance, that is the same bit error rate. So, we are going to essentially discuss today the receiver sensitivity degradation. That means, because of this practical constraints on the optical receiver, how the sensitivity of the receiver degrades, and to restore that sensitivity back, how much extra power has to be added into the system so that we get the same receiver performance or same BER. So, this is the quantity which is called the power penalty. That power penalty essentially is the extra power which has to be added in the optical system so that we get the same BER performance. And in this case, essentially we are going to discuss the power penalty due to the finite extinction ratio, which is related to non-zero optical level corresponding to the 0 level of the data. Relative intensity noise, what we call RIN, that is related to the laser noise at level 1, and then because of the inaccuracy in the clock, there is always the jitter, and because of that we have statistical fluctuation into the signal. So, we are asking, if the receiver had deviated from ideal conditions because of this, how much extra power has to be added, and that is the quantity we call as the power penalty. So, in this lecture essentially we investigate each of these power penalties. Of course, when one power penalty we are investigating, we assume that the other degradations are not there. So, at a time essentially we account for power penalty due to one effect, and then we say total power penalty will be sum of all the power penalties in terms of dBs. So, let us first look at the first power penalty, which is power penalty due to the extinction ratio. So, here what we are saying is that when the 0 level of the data is transmitted, the optical intensity is not 0. Now, there are certain reasons for that in a practical system. Firstly, if you recall, when we talked about the optical detectors, we had something called the dark current. This is the current which is because of the ambient light which is falling on the detector. So, even when no optical signal is transmitted, you will always have some light received, and that essentially gives you a small DC current corresponding to the 0 level of the data. In addition to that, if you recall, when we were discussing the laser characteristics, the laser diode characteristics, we have seen that it has a threshold current, and the speed of the device depends upon where the diode is biased with respect to the threshold current. So, if the bias is very close to 0, which is far away from the threshold current, then the device speed is less, because then it requires certain time to build the population inversion, and then the device goes into lasing action. So, to get a high speed, the laser diode is biased very close to the threshold current or just below the threshold current. What that means is, even in 0 data level condition, you still have the threshold current flowing into the laser diode, and therefore, there is a corresponding light emitted by the laser diode. So, the two effects, like the dark current and the biasing of the laser diode at the threshold current, they give you now non-zero power corresponding to the 0 data level. So, then we define a parameter what is called the extinction ratio, which is ratio of the power in the 0 level divided by the power in the 1 level. So, we have a parameter what is called extinction ratio, which is the power received by the receiver corresponding to 0 data level divided by the power received by the receiver corresponding to the 1 data level. In ideal situation, this quantity P0 is 0, so the extinction ratio is 0. Then we can define the average power, as we did in the last lecture for finding out the minimum detectable power. So, we can say this is the average power, say P REC, that is the mean of this. So, which is P0 plus P1 divided by 2. And the corresponding currents which we will have corresponding to these two powers, that will be the I0, that will be responsivity into P0, and I1, the current corresponding to 1 level, that will be responsivity into power P1. And then we can define the parameter Q for the data, which is equal to I1 minus I0 divided by sigma 1 plus sigma 0. So, let us say this quantity is denoted by R extinction ratio, REX. So, I can now take this quantity I1 common. So, this thing can be written as I1, which is R into P1. So, this is responsivity into P1 into 1 minus I0 divided by I1, which is proportional to P0 divided by P1. So, that is equal to REX. So, we have this quantity REX divided by sigma 1 plus sigma 0. If you substitute in terms of the average power, then this thing can be rewritten. So we can get a quantity 1 minus Rex divided by 1 plus Rex, that corresponds to this mean power, into 2 times P Rec into responsivity divided by sigma 1 plus sigma 0. Now, if we assume that the receiver is thermal noise dominated, then essentially this quantity sigma 1 and sigma 0, that will be approximately equal to sigma t. So, under the assumption that my receiver is thermal noise dominated, we can get sigma 0 approximately equal to sigma 1 approximately equal to sigma t. And then in this situation, we can get the average power required. This we can get essentially by inverting this expression. So, we can get average power received, which is 1 plus Rex divided by 1 minus Rex sigma t q divided by the responsivity. So, now we say that if the extinction ratio was 0, that is the ideal receiver, then we would require the average power in the data, which will correspond to Rex equal to 0. So, that quantity will be simply sigma t q divided by R. Whereas now, when the extinction ratio is finite, you will require little higher power PREC compared to the ideal situation. So, the ratio of PREC for a given value of Rex compared to when Rex was 0, that we can call as the power penalty. So, we can define the power penalty let us say it is denoted by delta Ex, that is in terms of dBs will be 10 log of P REC for a given value of extinction ratio divided by P REC for 0 value of extinction ratio. So, this quantity is a function of Rex, that is what we are writing here. So, substituting now for this quantity, the PREC 0 will be nothing but this. So, we get the power penalty in terms of dBs, that will be 10 log of 1 plus Rex divided by 1 minus Rex. So, one can essentially plot this function of the power penalty as a function of the extinction ratio. So, if you plot this, typically the plot will look like that. Here essentially we have plotted the extinction ratio starting from 0, that is the ideal receiver, to going up to 0.8, and this is the corresponding power penalty in dB. So, as we can see here that for an extinction ratio of about 0.2, we have a power penalty typically of the order of about 2 dB. And if you have extinction ratio of 0.4, then the power penalty is about 4 dB and so on. So essentially, if we say that for a receiver, the 1 dB power penalty is probably acceptable, then we can get corresponding to 1 dB extinction ratio, that will be approximately 0.12. So from this plot, we can get the numbers that this quantity delta extinction, that is equal to 1 dB for Rex of 0.12, and this will be as high as 4.8 dB for Rex is equal to 0.5. Typically, the extinction ratio would lie in the range of this. So, you will have a power penalty corresponding to the extinction ratio, which would be of the order of about a dB in the system. So, this is one of the power penalties when we design a practical receiver. The second power penalty which we have is the power penalty due to relative intensity noise, and that is, if you recall, that if the pulse has to be transmitted like this, because of the relaxation oscillations and all other noise present in the laser, the signal does not go like that. The signal essentially goes something like this. So, we are having some fluctuations in the optical intensity corresponding to the one level. This is the fluctuation which is called the relative intensity noise, and one can see that this effect essentially is a multiplicative effect, because this fluctuation which we are going to get into this amplitude, that will be proportional to the amplitude of the pulse. So, this noise, which is the relative intensity noise, this noise is a multiplicative noise. Because this noise is proportional to the amplitude of the pulse. So, what we do is we define now the variance for the relative intensity noise, and then this treat this noise in addition to the noise which is present because of the short noise and the thermal noise. And then we can ask a question, because of the additional noise which is there because of the relative intensity fluctuations, what will be the extra power added to the system to get the same BER. So, we define now the variance of the noise, which is sigma square. So, let us say this is the variance of the total noise. Sigma square, that will be equal to sigma short noise square plus sigma thermal square plus the additional noise which is the relative intensity noise, which we denote by sigma I, that square. Where sigma I we are denoting by the responsivity and the average value of the change in the input power. So, this quantity is the root mean square value of the input optical power multiplied by the responsivity, that is this quantity which is the sigma of the relative intensity noise. So, this one we can say that this is the responsivity multiplied by your P in into a parameter what is called the parameter for the relative intensity, where this Ri is defined as delta P n square to the power half divided by P n. Then what we do is we essentially find out now the I1 and I0, and now since we are considering only the relative intensity noise, we assume that the extinction ratio is 0. That means there is no power which is coming corresponding to 0 level, and in that situation then we can find out what is the average value. So, in this case, since the extinction ratio is 0 corresponding to 1 level, we have the current I1 that will be 2 times R into average value of the power, which is average P received. Then the Q factor which we have for this case will be Q, which will be equal to I1 minus I0 divided by sigma 1 plus sigma 0. Now, when one level is transmitted, we have all the noises present. We have short noise present, we have relative intensity noise present, and we also have a thermal noise present. Though maybe thermal noise may be negligible compared to this, but for sake of completeness, we can say that when one level is transmitted, all 3 noises are going to be present. Whereas, when 0 level is transmitted, since the extinction ratio is 0, we do not have short noise and we do not have relative intensity noise. So, we have sigma 0 which will be only sigma t. So, we have now a situation where sigma 1 will be square root of sigma s square plus sigma t square plus sigma I square, and sigma 0 will be only sigma t. And also, since we are assuming that the extinction ratio is 0, I0 is 0. So, we have this quantity is also 0. So, if you substitute now these parameters inside this, then you get this parameter Q, that will be 2 times R P average divided by this quantity, which is sigma s square plus sigma t square plus sigma I square to the power half plus sigma 0, which is sigma t, so equal to sigma t. And now, if you write this value of sigma s with the short noise, so sigma s is equal to 2 times Q responsivity average power to bandwidth to the power half. And we also have sigma I as we defined, that is equal to 2 times Ri, this is the relative intensity parameter, responsivity and P average. So, we can take this thing and substitute into this, and now note here that we have a PREC which is here, and also these quantities are now depending upon PREC. So, if we invert this thing and solve for PREC, we get the received power as a function of the parameter q, that will be PREC average, as a function of the RIN intensity noise parameter Ri, that will be equal to q into sigma t plus q p q square divided by the responsivity into 1 minus Ri square into q square. Again, from this expression, if we substitute Ri equal to 0, then we get the required receive power in the ideal situation. That means when the relative intensity noise is not present, and in the presence of this Ri, this quantity will be non-zero, and as a result we will require little more power. So we can define the power penalty in this case, which is the ratio of P received Ri divided by P received when Ri is equal to 0. And again, in terms of dBs, if you want, then we can define 10 log of that. So we have in this case the power penalty. Let us call it delta I, that is equal to 10 log of P REC bar for Ri divided by P REC for Ri equal to 0. So again, this term is same. So when I take a ratio, essentially this is the term which will cancel. So we get the power penalty, which will be 10 log of 1 minus Ri square into q square. Now for the acceptable level for the BER, as we know, this quantity q has to be at least 6. So if we say that we are working with a bit error rate of 10 to the power minus 9, this quantity q will be about 6. So for BER of 10 to the power minus 9, the q is approximately 6. So if you substitute into this, you get delta I, that will be 10 log of 1 minus about 36 into Ri square. We can plot this function again as a function of this parameter, the relative intensity noise, and the plot would look something like this. So we have got here the relative intensity noise plotted, and here we are having a power penalty in terms of dBs. So we see that as the relative intensity noise increases, the power penalty increases very rapidly, or in other words, the system degrades very rapidly. Now note here, the noise which you are indicating here is essentially indicating a value of sigma of the relative intensity noise. The peak to peak deviation of the noise is about 5 to 6 times sigma. That means one-sided deviation if you take on the data, then you are having approximately 2.5 times sigma deviation of the signal corresponding to mean level on one side. So when sigma is 0.1, essentially we have a peak to peak noise about 0.3 of this amplitude. If you make the sigma, which is about 0.2, that time we will have the peak variation, which is about 0.6, and then you will see that there are a large number of values which will be lying below the threshold value, which is half. And that is the reason, as the sigma for relative intensity noise increases, very rapidly the system degrades, and that's what essentially is shown by this figure, that by the time you go to a relative intensity noise of about 0.15, the power penalty is as high as about 8 dB, and beyond that the power penalty essentially becomes unmanageable. So, the power penalty due to relative intensity noise is a very sharp function, and that is the reason we have to keep the relative intensity noise as small as possible, right, inside the data. So, just to give few numbers, if we write for this, we have, let us say, delta I, that is equal to 0.02 dB for Ri is 1%, 0.01, that is equal to about 2 dB for Ri, about 10% or 0.1, and Ri is equal to infinity for Ri is equal to q to the power minus 1. As you see here, when this quantity Ri is q 1 upon q, that time this quantity will be 0, and then this will be infinity. So, that means if you are having the relative intensity which is 1 upon q, then the power penalty is very high. That means your receiver can never perform satisfactorily, because now the power penalty is infinity. That means to get the bit error rate of 10 to the power minus 9, we have to essentially increase the power by infinite dBs. Or in other words, if the Ri becomes comparable to 1 upon q, then we will never be able to achieve the bit error rate what we are desiring, which is 10 to the power minus 9. That is what essentially is shown in this by this plot, which very steeply increases as the relative intensity noise increases. So, we say that for this value, receiver will never achieve the BER. Required. So, that is the reason when we talk about the noises, especially this is going to come from the laser. So, this noise has to be kept low, so that the power penalty is again within the specified limit. Or in other words, if we say that maybe about a dB of kind of power penalty is okay, then the relative intensity noise should remain of only few percent level. Otherwise, the power penalty will be excessively large. The third power penalty we are seeing now is what is called the power penalty due to the timing jitter. Firstly, one can ask a question, why the timing jitter gives a noise which will affect the bit error rate. One can again go back to the data, and one say that if we had a pulse which is like this, after all when the pulse is detected, we have a sampling time at which essentially we ask whether signal is below threshold or above threshold, and depending upon the decision we assign the level either 0 or 1. So, if you are having a pulse which looks like that, even if you are having a small jitter in the clock, that means if this pattern wobbles little bit, it does not make any difference because you are going to always sample this amplitude. However, what happens in practice because of the finite bandwidth of the system, we have now a pulse which is rather distorted. Also, to reduce the intersymbol interference, we may not transmit a pulse which is rectangular in shape, we may have some other form of the pulse. So, let us say the pulse which is transmitted or which has become after a distortion looks something like this. Something like this. And then over and above, the noise is superimposed on this. So, now if we are having now a timing jitter, that means on this function, the sampling point essentially is having a random fluctuation. That means sometime we sample here, sometime we may sample here, sometime we may sample here, and so on. Now, since this function is not constant over this time when I am sampling, when I sample here, we get an amplitude which is this. Whereas, if we sample here, that means if my clock had drifted little bit, then we sample the amplitude which is this. What that means is now that we are having now a random fluctuation in the intensity or the amplitude of the signal because of the jitter in the clock or jitter in the sampling time. So, the sampling time jitter essentially gets converted into the corresponding amplitude fluctuations. So, basically what we are seeing here, that the statistical fluctuation which you are having in the sampling time or in the clock, they essentially get converted into equivalent relative intensity noise. Because here also how much fluctuation you are going to get will depend upon the amplitude of the pulse. So, we have got here equivalent some kind of relative intensity noise, that is because of the fluctuation in the sampling time. So, now we can define the parameter, assuming that again the current is 0 corresponding to 0 level and thermal noise is also small, there is no thermal noise and all that. We can define this parameter now Q, which will be I1 minus this quantity which you have got delta I due to jitter value divided by sigma t square plus sigma j square, where sigma j is the noise because of the jitter or converted into corresponding relative intensity noise 1 by 2 plus sigma t. So, here we are having essentially this quantity sigma j is the RMS value of the fluctuation of the current due to the sampling time fluctuation. Now, obviously, what fluctuation we are going to get in this and its statistical variation will depend upon the shape of this pulse. So, if you have a pulse shape which is rectangular, then obviously there is no fluctuation in this. So, we do not have any jitter noise. Whereas, if you have a function which looks like that, then we will have the corresponding jitter noise. So, essentially what we are saying is, because of this fluctuation here, let us say this function is given by a function, let us say, which is h of t. And let us say the fluctuation which we have in sampling is given by delta t. And let us say this is the peak, is the time which corresponds to 0. So, I measure at the peak, this is the best sampling time, and because of the jitter I can sample on either side, and time deviation could be delta t. So, then the amplitude change which we are going to get here will be essentially delta ij, that will be I1, which corresponds to this level, into h of 0, that corresponds to t equal to 0, minus h of delta t. So, this is the function now h of t, that is the one which essentially is going to give me now the change in the amplitude. So, this quantity which we got here, that quantity is nothing but delta I jitter. Now, we can choose different pulse shapes. So, either the pulse shape could be cosine square, but generally for the reduction of the intersymbol interference, we use this pulse shape. So, let us say I use this function which is the cosine square function. So, we get h of t is cos square of pi b t by 2, where this quantity is the bit rate. So, the pulse is no more rectangular pulse now, the pulse is having a shape which is a cosine square shape. And the corresponding transfer function you write, which reduces essentially the intersymbol interference. We get the raised cosine filter for this pulse shape. So, we get now raised cosine filter for minimum intersymbol interference ISI. If you do that, then the transfer function for this receiver would be given as one plus cosine of pi f by b by 2 for frequencies less than b and equal to 0 for frequencies greater than or equal to b. So, this is the filter which is normally used in the receiver to reduce the intersymbol interference, and for this then we can get this function what is called the impulse response ht, which is given by sine of 2 pi bt divided by 2 pi bt into 1 upon 1 minus 2 bt square. So, assuming that now this quantity here b into delta t, which is the time fluctuation, is small compared to 1, what essentially we are saying is, compared to the bit duration, compared to the bit duration here, if the time fluctuation is small, so delta t is much smaller compared to this bit duration, that essentially is given by when b delta t is much less than 1 for this condition. We can get the change in the current for this pulse shape, that will be equal to 2 upon 3 pi square minus 6 into b delta t whole square into the mean current level I1. So, you have this quantity here delta ij, that is what we are trying to find out for this function, and I1 is the current corresponding to one level. So, that is now the fluctuation which we have. Assuming that the distribution of this fluctuation is Gaussian, then we can calculate the density function as a function of delta t. That will be given 1 upon root of 2 pi. Let us say tau j is the standard deviation of the fluctuation of the sampling time, e to the power minus delta t square divided by 2 tau j square. And we can find out the corresponding now the density function for the current for this. So, we essentially get the density function for delta I j, that will be equal to pi some parameter which we define b delta I j I1 to the power minus half e to the power minus delta I j divided by b I1, where this parameter b is 4 by 3 into pi square minus 6 into b tau j square. So, once I have this density function now for the current, we can now go back and substitute into the noise expression. We can find out what is the relative intensity noise produced because of the timing jitter. So, if we do that, then we can get now the received power P for a given Q. And now this will depend upon this quantity here, which depends upon this tau j, which is the standard deviation of the timing fluctuation or jitter in the clock. So, this is now going to be a function of this parameter b, that is equal to your sigma t into q divided by responsivity r into 1 minus b by 2 divided by 1 minus b by 2 whole square minus b square q square by 2. So, again by substituting this quantity b equal to 0, we get the power required in the ideal situation. So, we essentially have now the PREC corresponding to b equal to 0, that is the ideal condition, and now because of the finite value of b, which is related to the variance of the timing jitter, we get the corresponding power penalty. So, we can define now the power penalty delta j, that is 10 log of again the same thing, which is P received for B divided by P received when B equal to 0. So, essentially this is the quantity If you take 10 log of that, that will give me the corresponding power penalty. So, if you plot this function as a function of the timing jitter now, or this product b into tau j. So, we have a parameter here b into tau j, and we have a corresponding power penalty which is plotted here. Again, we see here the power penalty increases very rapidly, and by the time we have this product about 0.2, the power penalty practically becomes infinity. And that we can see from essentially from the eye diagram, that if the sigma of this quantity is about 0.2, that means the clock peak to peak wander will be over the bit duration, and then essentially the pulse will not be sampled properly. So, we can see from here that for delta j of about 2 dB, this parameter b into tau j, that should be approximately 0.16, and as we saw, this will become infinity when this parameter is greater than 0.2. So, essentially what we are saying is timing jitter should be small, and a value of about few percent timing jitter may be acceptable to give you a power penalty of between 1 and 2 dB. So, what we have seen in this lecture essentially is that because of the non-ideal situation of the optical receiver, like you have a finite extinction ratio, you have the relative intensity noise because of the laser fluctuations, and you have a timing jitter, you have to essentially add extra power into your system to achieve the same bit error performance. So, we have seen here three major parameters or three major effects which contribute to the power penalty. So, total power penalty will be sum of the power penalties of this, and that is the reason when we design an optical link, we have to take this thing into consideration and essentially supply more power to the system to overcome these power penalties, so that we can get the satisfactory receiver performance.